That's right. The number of walks from 1 to 2 is the entry 1, 2 and 2, 1. Since the matrix is symmetric. So therefore, then it gives you the number of walks from one square to the other by calculating the nth power of the adjacency matrix, which we have just found. Now, let us introduce a parameter called theta. Well, we will say that theta is 1 if it's a closed walk, and theta is 0 if it's not a closed walk. Say I want to go back from starting from 1 and ending from 1, then it's a closed walk. In the case of a closed walk, I will say theta equal to 1 and theta equal to 0 if I am not ending at the same starting point. So one can say that since the number of, for a closed walk, it is 1 by L times L minus 1 power n plus L minus 1 plus times minus 1 power n. And for an open walk, it's 1 by L times minus 1 power n. So one can simply plug in the theta value here. If theta is 1, you get the following. Here, if theta is 0, you get the following. So if you put theta here, theta L, you get, if theta is 0, you get this, and if theta is 1, you get the following. So with introducing a parameter like theta, you can close the formula for both open and with considering both open and closed walks. So you have two parameters, whether the walk on one particular component will be open or closed and the length of that particular component. So for a k-dimensional board, you have the lengths L1 to Lk and the parameters theta 1 to theta k, where theta 1 will decide whether starting and ending points are matching or not. So if you have x1 till xk and y1 till yk, now the question will be framed as, I'm starting from x1, x2 till xk as my starting vector, and my final vector is y1, y2 till yk. Now, how many ways can I move from this vector to this vector in n moves? Now, one criteria will be to find out if any of these y's are equal to any of the x's. Now, that is why we have Boolean theta 1 till theta k to decide whether x1 is equal to y1, x2 equal to y2, and so on. So theta 1 will be 1 if x1 equal to y1, and theta 1 will be 0 if x1 is not equal to y1. Then you have an open walk from x1 to y1. So you have, what you ultimately have is parallel complete graphs where say L equal to 4 and K equal to say 3, then you have 3 K graphs. And in each move, you move in one graph from one vertex of that particular graph in parallel. So you have, let's say, horizontal, vertical, and right. Let's say left, right, top, bottom, and up, down. So each move will either be in one of these components. Either it will move in vertical, horizontal, or in the top and bottom. This is for K equal to 3. So this is how we will solve the problem. Now, say in a two-dimensional board, either you move in horizontal or vertical. Now, say I move R moves. There are n moves. I move R moves in horizontal. That means I move n minus R in vertical. So there are n factorial by R factorial, n minus R factorial times number of ways to move in one component. Sorry, crash. Yeah, number of ways to move in one component. Say F1 of n is the number of ways to move in one component of L1 and F2 for L2. Then you have NCR F1 R and F2 n minus R. This will give you the number of ways a rook can move in two-dimensional board of L1 cross L2 with R moves in horizontal and n minus R in vertical. Now, this will give you a number of ways a rook can move from starting to the ending point in two-dimensional board based on parameters of theta1 and theta2. Theta1 and theta2 will decide whether the rows are same, the columns are same or not. Now, by computing the following, we end up having 1 by L1, L2 times, let us compute the following. Let us compute the following. Well, NCR 1 by L1, L2, L1 minus 1 power R, n minus R plus theta 1 L1 minus 1 power minus 1 power n minus r times L2 minus 1 power r plus theta 2 L2 minus 1 times minus 1 power r. Multiplying the following gives L1 minus 1 power n minus 1 L2 minus 1 power r plus theta 1 L1 times minus 1 power n minus r L2 minus 1 power r plus theta 2 L2 minus 1 times minus 1 power r times L1 minus 1 times n minus r power n minus r plus theta 1 L1 minus 1 power n. Now computing the following will give you L1 plus L2 minus 2 power n binomial and theta 1 L1 minus 1 by L1. Yes. Theta 1 minus 1 times L2 minus 2, again binomial, times L1 minus 2 plus theta 1, theta 2, theta 1 L1 minus 2 power n. You get the following. This is your result. Now, if we substitute L1 equal to L2 and theta 1 equal to 0, theta 2 equal to 0, you get the following. You get 1 by 64 times 14 power n minus 2 into 6 power n plus minus 2 power n. Taking 2 power n minus 6 common, you get the following. Now, now if we assume R2D of n as number of ways a rook can move in a two-dimensional board with theta1, theta2 as a parameter, and R3 of n for theta1, theta2, and theta3 as a parameter for three-dimensional, and RKD for up till theta k for a k-dimensional board, the number of ways a rook can move in n ways. If we assume this as the notation, then we can simply say that R3D of n is simply function NCR R2D of n, R2D of R and F3 n minus R, and so on. RKD of n will simply be NCR Well, it's simply because it will move in the k-1 components or in the kth component. If it moves if it takes r moves in the k-1 components, x1 till xk to y1 till yk, it either moves xk minus 1, yk minus 1. Well, either it moves in either of these in r moves and n minus 1 r moves in this. If it moves in r moves in this till x1 till x minus k x of 1 and till x of k minus 1, it must move n minus r in the kth component. So we get the following. Now, now let us introduce a new concept of combinatorial binomial convolution. Say, for calculus, convolution is simply a b f of t g of x minus t dt. This is f star g of x. This is convolution for calculus. Now, binomial, let us define f star g of n as that f star g of n as NCR f of n minus r g of r as the binomial sum of these products. Now, if we change n and r, n minus r and r, this interchanges. Therefore, f star g is also g star f. Now, assume f as a linear combination of exponentials. Say fi of n is alpha I, alpha j times beta I, beta j, and j, I would say assume f as a linear combination of some powers of integer powers. Say you can take, for example, f I of n as say f lambda of n as say 3 times 5 power n plus 2.5 times 8 power n plus 7.5 times 3.72 power n, for example. This is your linear combination of powers of n. Now Si here is simply a set of integers. Okay. So we assume this as your Fi, and now let us, if we calculate Fi star Fj, we will get NCR summation mu belonging to Si alpha I mu beta I mu power n power R summation V Si alpha I V times beta j V power n minus R. If you multiply this, since multiplication is distributive, you get the following. Now, we can change the summations. This is nothing but because of binomial, we get the following. So what we have done, we have used distributive property of multiplication to combine summation. Then we have brought the NCR inside, and we have combined, get the following. Here is your Fi star Fj. Now, what about Fi star Fj star Fk? Then, well, again, it will simply be NCR summation mu 3 belonging to Sk lambda I mu 3, beta I mu 3, beta k, sorry, k, n minus r times times summation mu1 belonging to Si, mu2 belonging to Sj, alpha I mu1, alpha j mu2 times beta I mu1 beta j mu2 power n power r. So this will again be mu1, mu2, mu3 belong to Si, Sj, Sk respectively, alpha I, alpha j, alpha k with the mu's, with beta I, beta j, beta k respectively. Well, because of interchangeabilities and commutativities, one can also say this is associative. This is nothing but also one can get the associative property as well. So by iteratively, you get the following: that Fi, F1 star till Fk star convolution is simply but mu1 till mu k belong to Sk respectively, mu1 belong to S1, alpha 1 mu1 till alpha k mu k, and beta 1 mu 1 till summation beta k mu k power n. This is your convolution formula. Now, using this, we simply substitute Si as 1, 2 and alpha I1 as 1 by L1, 1 by Li, and alpha I2 as 1 by Li times theta I Li minus 1, and beta I1 as Li minus 1, and beta I2 as minus. Substituting this, one can get RKD as one can get this. Well, how? Well, a hint is that since each of Si is an element, is a set of two elements, so each of the mu i's will be either 1 or 2. So that means there are 2 power k such possibilities. And subset, so that means S belongs to the power set nk here. This is the implication of this, which is nothing but 2 power k. The number of such subsets is 2 power k. Since there are, okay, so nk is nothing but number of elements from 1 to k. So subset of number of elements from 1 to k is 2 power k. So there are 2 power k possibilities. So let's elaborate on this. That why we get this. From substituting this, why we get this from